Good afternoon, dear students. In electrochemistry, today we are going to see about the galvanic cell notation and then EMF. Okay, galvanic cell notation. So, for example, simplest galvanic cell, Daniel cell. I am taking Daniel cell. And the Daniel cell, if you see, certain 2 plus solid aqueous. This is a cell notation of the Daniel cell. Cell notation. Okay. What is there? We are going to explain one by one. First of all, this is called anode region. This is cathode region. Electrochemical cell, anode region and cathode region. Here what is happening? The anode of cell. We can say anode of cell. Here cathode of cell. Then what is happening here? Oxidation compartment also. In the anode what is happening? Oxidation is always happening. Here reduction will happen. Here you will get a reduction. Okay. So how we can write this? First of all, metal. Okay. Then metallic ion. At the oxidation side, that anode compartment, you have to write first metal, that is zinc electrolyte, zinc electrode, then electrolytic solution, the ionic form, Zn2 plus. Okay. Then you have to mention what is the state here. Zinc is solid. This is the aqueous form, electrolytic solution, that is aqueous. Then you can mention that the concentration of that aquatic solution. If it is a 1 molar concentration, 1 ml. Okay, like this. This is anode of cell side. Then what happened to, what is the, this is though, so the single vertical line is a phase boundary between the metal and metallic ion. Metal and metallic ion. Zinc metal and metallic ion. So metal and metal ion is separated by phase boundary, single vertical line. The single vertical line is used to separate the metal and metal ion. Okay. In that, in the oxidation side, you have to write the metal first, then metal ion, because it represents the oxidation. What happens in a Daniel cell? Zn gives a Zn2 plus 2 electron. What is happening? Oxidation. Here Zn becomes Zn2 plus. So we need to write first metal Zn, then Zn2 plus. Then double vertical line. What is double vertical line? Double vertical line shows the salt bridge. Salt bridge. Salt bridge is neutralizing. For example, if you draw a Daniel cell, this is a beaker line. This is zinc rod, electrolytic solution. This is SO4, electrolytic solution. That is zinc. Okay, that's solid form. Voltmeter, the same way. If you have a diagram like this. Copper sulfate and copper rod. This is voltmeter. So in that neutralizing purpose, there is a bridge. This is called a salt bridge. This is a Daniel diagram. This is Daniel cell notation. Here this is called a salt bridge. It can be used as a paper, even the filter paper can be used for this salt bridge. Tip into the solution. As you know, in the morning itself we have seen that how the reactions carried out. It is Zn pulling the electron. It pushes the electron towards the cathode. The potential difference, the digital voltmeter, we can measure the potential difference. Here the electron comes to the pulling the electrons towards the anode, pushes towards the cathode, then it is pulling towards the cathode here. Okay, oxidation take place. Oxidation means the release of electron. Reduction takes place, that is a gaining electron. Loses electron, gaining electron. Okay, let it be. See, come here. While writing the cathode side what happened? Reduction means copper 2 plus become copper. So here also metallic iron and metal. Here, while you write in a cathode compartment, you always write the metal ion first, then the metal. But whereas in an anode, metal first, then the metal ion. Whereas in a cathode compartment, you have to write while it is taking reduction, ion first, then the. You need to mention what is the aqueous conditions, states, and all everything. The aqueous condition, the concentration, for example, 1 molar concentration, everything should be noted down. Now after this, this is called salt bridge, which is connecting the two compartments. Above this is a voltmeter to measure the potential difference. This is called cell notation. Okay, by this we can write this zinc is oxidized, so zinc first oxidized to zinc 2 plus, then salt bridge, copper reduced, so copper 2 plus 2 copper. Okay, solid, this is aqueous. Okay, if the concentration 1 molar concentration like this, what is the concentration? Everything should be mentioned. This is called a complete cell notation. For example, we can have one more example here. Take a chromium. 2Cr plus 3Cu2 plus. It gives 2Cr2 plus 3Cu. This is cell reaction. It is not a cell notation. There is a difference between the cell reaction and a cell notation. This is overall cell reaction. How the reaction takes place, sir? What happened to chromium? Chromium 2Cr loses electron, becomes 2Cr3 plus, and giving a 6 electron. Okay, 1 Cr loses 3 electrons. Totally 2 Cr chromium is there, so totally 6 electron loses. What happens? This is process called oxidation. Oxidation where it takes place at anode reaction. This is called anode reaction. The process is oxidation, anode process, anode reaction. Then what happened to copper? 3Cu2 plus. It is gaining the 6 electron which chromium is released. Then it becomes a 3Cu2 plus 3Cu, because 3Cu2 plus gains 6 electron. 1 copper gains 2 electron, means it will become copper. 3 total 6 electron copper. Okay, this is a reduction. The reduction where it takes place at cathode. So what is the overall reaction? This is called a 2Cr plus 3Cu2 plus gives 2Cr3 plus 3Cu. This is the overall reaction. Okay, overall reaction. Still now we have written only cell reaction, not cell notation. Now I am going to write a cell notation. After seeing these chemical reactions, let me conclude that here chromium is oxidized, whereas copper is reduced. Okay. Then what is the electrode, anode compartment? What we need to write here? Chromium is converted to Cr3 plus. Okay. So chromium is oxidized, chromium solid, that is aqueous and 1 molar concentration. Then salt bridge to connect these two, salt bridge. Then I am writing what happened to copper. Copper 2 plus, that is aqueous 1 molar concentration. It is Then single vertical line to mention that this is called cell notation of this above cell reaction. So you have to have a difference between cell reaction and cell notation. Sometimes the question may be asked, write the cell notation for Daniel cell like this, or they will give a 2 electrodes, write the cell notation. Sometimes they will ask cell reaction. What happened in an anode, what happened in the cathode, like this if you ask, you have to ready to write this. This is a galvanic cell notation. Let's move on to the EMF. What is called EMF? Electromotive force. Electromotive force. Electromotive force. EMF. It is nothing but, see, look at the Daniel cell. I may explain the what is the EMF of the cell. See here, what happened? At the anode, oxidation takes place. Oxidation takes place means the electrons is pushed out from that electrode. See, it is pushing 2 electrons towards that cathode side. What is the potential difference? It can measure by the digital voltmeter. Voltmeter, we can measure the force of the electrode potential difference. Then here it is a tendency to gain electron, receive the electron. That tendency we can measure it here. That is pulling the electron towards the cathode, pushes the electron towards the from the anode and pulling the electron towards the cathode. How? Here pulling the electron from this anode. This is a reduction. So the reduction takes place. This force is how the electron pushing and pulling. That force is called electromotive force. That force is called electromotive force. How electrons are pushing from anode and pulling from the cathode, that is called electromotive force. This is called electromotive force. So E cell, E naught of this cell, E cell, electromotive source of cell is, that is E naught of the oxidation plus E naught of the reduction. Like this we can write, or we can simply write this E naught left plus E naught right, or otherwise E naught anode, anode E naught plus E naught of cathode. These are the different way you can get. It is sum of the 2 of cells. The electrode potential is nothing but a sum of the 2 of cells. The electrode potential of the sum of the 2 of cells. Here one potential will be there, here one potential will be there. Total E cell will be there. Sum of these 2. That is why E oxidation plus E reduction, or E left side and right side, that means mentioned, or sometimes E anode and E cathode. Among these 3 formulas you can use in English. Then let us move on to how to calculate the single electrode potential. There is no way, it is impossible to calculate the single electrode potential. Single electrode potential, simply zinc is given. What is the electrode potential? You can ask. That is a cell is a combination of 2 of cells. Okay, that is anode compartment and a cathode compartment. When it is both are combined, only we can get a cell EMF. But how to calculate the single electrode potential? It is impossible to calculate it in a direct manner. There is some way. That is, we need to help of the reference electrode to calculate. We need to construct a cell first. Cell is combination of 2 of cells. If you take a single electrode potential, it is impossible. So, but by using the reference electrode, we can calculate the single electrode potential. For reference, what is the quality for the reference electrode? The standard value should be there. For EMF, that is E naught value should be 0 like that. That is a standard condition is there. That's why we have a standard hydrogen electrode She, that is called a She. Standard hydrogen electrode, that is called a C. We have C S H E, that is called standard hydrogen electrode. That's why we call this C. What is the specialty? Standard stand for standard conditions. What are the standard conditions? 1 molar concentration and 25 degrees Celsius, 1 atmospheric pressure. These are the standard conditions to be used in electrochemistry. Okay. So this is a standard condition should be maintained. Hydrogen electrode. What is the specialization? The standard hydrogen She, that is E naught of the C. E naught of the sheet is always 0 volt. This is special. Okay. What is one more specialization in that? It can be used both oxidation and reduction. For example, if we take a 2 H plus 2 electron, it gives H2. That is aqueous form. It is a gaseous. Okay, that is 1 atmospheric pressure. Then 1 molar concentration. What happens are here? Here electrons are gained. So this is called the cathode reaction. You can connect the sheet at the cathode also. If you connect the cathode, the reaction will take place like this. If you connect the anode, H2, what will happen? 2H plus 2 electron. Oxidation takes place. It is anode reaction. So here 1 atmospheric and the gaseous state, aqueous state, 1 molar concentration. Okay. So if you fix it in the sheet, that is standard electrode, into the cathode, the reaction will take place like this. If you fix it in the anode, it will be reaction takes place. So in both sides we can take. This is specialization of sheet. We can use as a cathodic cell. Same way in the anodic side also we can use the sheet. Okay. Then the construction of sheet. How the construction of sheet is there, sir? See, this is a container like will be there. That a platinum electrode, because hydrogen is a gas, no, so the electrode should be a metal strip, that is platinum rod. Always electrode means that should be a metallic strip. But we are using the hydrogen electrode. There is no, hydrogen is not at all a metal. So metallic strip, we are using platinum. Platinum is inert in nature in this case. So we are using the platinum electrode. Here it is filled with electrolytic solution. What is the electrolytic solution? The solution which contains that same part of ion. Hydrogen is contains HCl I am taking. 1 molar concentration of HCl is a electrolytic solution. That is platinum electrode. Here 1 atmospheric H2 inlet. This side H2 outlet. H2 in and H2 out. And H2 in, there is a bubbles created. This is a hydrogen gas. Bubbles will come. So that is 1 atmospheric pressure. Okay. This is a setup of a sheet, standard hydrogen electrode. When a gas is passed through the electrolytic solution, that is a 1 molar HCl, at 25 degrees Celsius this should be maintained. At 25 degrees Celsius, when you passes the H2 gas here, the bubbles will come. Then afterwards, the reaction takes place according to the usage. If you can use as a cathode or as an anode. If it is used as a cathode, this reaction will carry out. Okay. If it is used as an anode, this reaction will be carried out. In both cases, what is the electrode potential? Whether you are using the anode or cathode, the electrode potential E naught C equal to 0 volt. This is specialization. That's why we are referring this as a reference electrode. By using the reference electrode, in order to calculate the single electrode potential, we need a reference electrode, because the cell is a combination of 2 half cells. Within the 1 half cell you cannot calculate. So one is we need which cell we need. That is you can keep whether the side of anode or cathode. The another one reference, the reference electrode should have 0 electron volt. 0 volt, it is very easy to that. Then you can calculate like this. Then what about the EMF dependence? The EMF will be depending upon. The EMF, that is electromotive forces, depend upon these are the factors which nature of electrode. EMF depends on the nature of the electrode and the concentration of electrolyte. Concentration of electrolyte. That is solution, liquid conductor, electrode, then the temperature. So these are the factors which influence or which affect the EMF. We need to consider the nature of electrode and the concentration of electrolyte, that is solution. Then the temperature, at which temperature it is operating. These are the factors which affect the electrode. For example, when EMF is produced, we can say 1 joule of energy is released. 1 joule of energy is released when a 1 volt current into 1 coulomb charge is applied. 1 volt and 1 coulomb charge is applied. When a 1 coulomb current and 1 volt, that is a quantity of current, 1 coulomb, and the charge is 1 coulomb and 1 volt is applied, you can get a 1 joule amount of energy is released. Okay, it's for explanation. And see, now I am going to illustrate how C's works. Okay, that we will see now. By using She, how we can calculate the electrode potential. For example, zinc electrode potential I am going to calculate. For example, if when a zinc rod is dipped into zinc sulfate, okay, there is a potential difference. There is the electron will pushing from this here digital voltmeter. If you keep it, this is hydrogen, that is She is connected. Now what is the role of C is, under salt bridge everything should be mixed. Salt bridge is drawn. Salt bridge. What is the role of C? Cathode compartment. You know, cathode is there. Always right side cathode, left side anode. What happens? Oxidation. It is a reduction. So what is the potential here? We can expect that is a oxidation potential. This side potential, reduction potential. Okay, this is oxidation potential, this is reduction potential. Now the complete cell we have. That is, our purpose is to mention the zinc electrode. Zinc rod is going to, what is the electrode potential of zinc. But I have constructed with the standard electrode potential, reference electrode. So I have complete cell. Okay. Now we have completed. If you measure this, what happened to here? So cell reaction also we can write. How we can write a cell reaction? First of all, you have to write cell reaction, then cell notation. These two things you have to write. Cell reaction, zinc 2 plus, zinc is oxidized, so zinc 2 plus is 2 electron. Because anode oxidation. Okay. Then what happened to the cathode? Cathode, She is there. What is the cathodic reaction? It gain 2 electron in zinc rod, form a H2. So the states should be mentioned here. Solid, aqueous. Aqueous means what is the concentration? This is 1 molar concentration. Okay. Then H2. Here also aqueous, 1 molar concentration, 1 molar, that should be mentioned. So that is 1 molar HCl is there. You know, She, under the construction we have seen now 1 molar H2 is HCl, and H2 also present as a bubbles. H2 and platinum is the platinum electrode is there. This is platinum electrode. This rod is a platinum rod. H2 is 1 atmospheric pressure. The gas, since we need to give the atmospheric, 1 atmospheric condition. So H2 gas is, this is 1 atmosphere. Then this gas is should be mentioned. Okay. Oxidation and reduction. Oxidation reduction takes place. Then overall reaction, Zn plus 2 to cancel the 2H plus gives Zn 2 plus H. This is overall cell reaction, not cell notation. By based on the cell reaction, I am going to write a cell notation here. What is the cell notation? What is the anode compartment? Anode compartment, what is happening? Zinc is oxidized. So first of all, we write metal, zinc, then metallic ion, zinc 2 plus, The metallic nature is solid here, aqueous, 1 molar concentration. These two. Everything should be mentioned. Cell rotation. Cell reaction, it is cell rotation, I am not right. Salt bridge is there, so salt bridge double vertical line. It is meant for salt bridge. Then, what is happening? Anode, cathode. Cathode side what is here? 2H plus, aqueous. Then you are writing the platinum here, bar in brackets platinum. There is a rod. Platinum rod is there, no? So platinum we have to mention. This is inert electrode. 1 atmospheric pressure. See here, 1 molar concentration, aqueous form, and single vertical line to the H2 gas, 1 atmosphere. So this is cell notation. This is cell reaction. Okay. Now, how to calculate the EMF? What is the EMF? EMF equal to or E cell. E not of the cell. There is complete cell. From the complete cell, we are going to get this value. E not of the cell, that is E anode, E not of anode plus E not of cathode. Or E not of the oxidation is E not of the reduction. While you measuring the zinc having the 0.76 volt voltage difference, the digital voltmeter saying that 0.76 volt. That means the oxidation potential is given, that is E naught 0.76 volt. What is the reduction? Reduction we take She, that is standard electrode. Standard, what is the value? That is 0 volt, always 0. Whether it is used as anode or cathode, the standard, this value is 0 volt. That's why it's used as a reference electrode. So total net is equal to 0.76. That is single electrode. That is Zn2 plus. What is happening? 0.76 volt. This is a single electrode potential of zinc. By using She, we are calculating. Sir, what is there is oxidation. So this is called oxidation potential. This is called oxidation potential. It is always the tendency of the zinc is to go oxidation nature. Whereas if you alter this, what happen? So critically, if you think, sir, what happen if I place the She into anode side and this will be in a cathode side? Okay, the same reaction will ditto, but the sign, if it is a anode, it is in the anode side. You want a cathode, zinc as a cathode. If you use a cathode side, you want to use a cathode side, nothing is there. Zinc 2 plus now zinc, the sign will be changing, minus 0.76 volt. Value will not change, but the sign will be altered because it is interchanged. So oxidation potential positive value, that is the reduction potential. That is the oxidation potential of the zinc electrode, that is the reduction potential. Oxidation potential positive, reduction potential negative. As well as if you use copper here, copper also you may get a 0.44. If you, for example, if you use copper, that is 0.44, that is the reduction potential. If you change it, then it will be minus. That is impossible. If you want to change and calculate, the sign will be changing. Reduction potential, oxidation potential. The data, there is a electrochemical series is there. You may find the data. This and this. This is how we can calculate the single electrode potential. And then now we are into the conclusion. Like in a Daniel cell, Daniel overall cell now. For Daniel cell E naught calculation, we can do Daniel cell E cell equal to E naught of anode plus E naught of cathode. Okay. Anode oxidation electrode for zinc. What is the anode? Anode is a zinc electrode. There will be then Zn2 plus. Whereas copper will be cathode in a Daniel cell. This is calculation of Daniel cell. Daniel cell. Cathode is copper 2 plus 2 copper The value already in the given, if you experimented data, if you find that 0.76 plus 0.44 volt. So for copper, 0.44 with 0.76, that is oxidation potential, this is reduction potential. When you add this 1.1 accurately, or otherwise most probably 1.017 like this will go to come around 1.1 volt. This is a the Daniel's calculation. Zinc 0.76, 101. This is how the cell notation, and today we have seen this how to write the galvanic cell notation and from the cell reaction. After that we have seen EMF. What is the EMF? Electromotive force. Electromotive force, that is the pushing and pulling of electron from the anode and cathode. That is called electromotive force, the force acting them. That can be calculated from voltmeter. The digital voltmeter if we keep, suddenly you can find that how many the potential difference you can measure it. Then EMF depends upon the nature of electrode and the concentration of electrolyte and then temperature. These are the factors which influence in the EMF. Then how to measure the EMF? EMF can be calculated from the E cathode plus E anode, that is E reduction plus E oxidation. From this we can calculate the EMF. The Daniel cell EMF we can calculate it like this. After that, how to calculate the electrode potential of single off cell? That is a single electrode potential. It is direct way. There is no method to calculate. It is impossible to determine that single electrode potential. But by keeping that reference electrode, we can construct the cell. From the cell, we can calculate the EMF of single electrode potential. For that, we need a single standard electrode. That is called a C we are using. C is a standard hydrogen electrode. It is used as a reference electrode. What is the speciality? It is a E0 value 0. Whether it can be used as a anode and cathode as well as in both cases we can use. In both cases you find 0 volt only. From this, if you construct the cell, complete cell which you want. For example, is zinc electrode. You want electrode potential mean zinc and hydrogen you combine to frame a cell like this. After this, you can calculate that single electrode potential. Okay, thank you.